Picture this. You are doing, say, 70 miles per hour down the interstate in a modern dual-motor electric vehicle.
Right, just a normal commute.
Yeah, exactly. The radio is playing, the climate control is, perfectly set, and as far as you know, you are sitting on top of the absolute pinnacle of modern automotive engineering.
Because you basically are, these vehicles are essentially rolling supercomputers at this point.
They really are. And they operate under ASIL D, right? Which is the absolute highest functional safety standard in the automotive industry.
Yep. Automotive Safety Integrity Level D, it is the gold standard for keeping you alive.
Right. And a core part of that safety rating relies on what engineers call a fail operational architecture.
Which is a fancy way of saying the car expects things to break and has a plan for it.
Exactly. In plain terms, if one of your two motors violently fails while you're at highway speeds, the system is supposed to, gracefully isolate that dead motor in a matter of milliseconds.
Milliseconds, yeah.
And then transfer the driving load to the healthy motor and basically allow you to smoothly drive to the shoulder.
Right, they call it limp-home mode.
Limp-home mode, yeah. It's the ultimate digital safety net.
And it's the foundation of the trust we place in electric powertrains. We implicitly trust that the system can manage its own failures without us even really noticing.
Right. But today, we are looking at a highly technical, honestly incredibly intense engineering document that asks a really terrifying question.
Oh, yeah. This one kept me up a bit.
What happens when that digital safety net catches fire? What happens if the transition to limp-home mode just completely fails?
It's bad.
Okay, let's unpack this. We are diving deep into a catastrophic failure mode, officially designated as E04. Single Motor Degradation Mode invalid.
Single Motor Degradation Mode invalid. Yeah, the consequences outlined in our sources are just stark.
Yeah, if this specific mode triggers, it leads directly to a total loss of propulsion.
Or worse.
Right, worse. It can cause an unexpected brake lockup.
At speed.
Yeah, imagine driving at 70 and the wheels just suddenly freeze because the internal logic of the car collapsed under the weight of a hardware failure.
What's fascinating here is that to truly understand the sheer violence of an E4 failure, we need to completely shift how we visualize the car.
Okay, how so?
Well, we have to look past the sheet metal and the touch screens. If we visualize a high-tech engineering schematic that suddenly morphs into this thermal and electromagnetic imaging display of the EV's powertrain, we start to see the reality of the situation.
Oh, wow.
Yeah, we are looking at a battle fought and often won or lost in literal microseconds.
Microseconds.
Right. It's a war fought simultaneously across physical space, extreme electrical transients, and deep within the multi-core software itself.
And is a war most drivers have absolutely no idea is happening right beneath their feet.
None at all.
So to understand how engineers fight this war, we first have to understand how a single motor failing can essentially act almost like a rapidly spreading virus.
That's a great way to put it, yeah.
Like it infects the healthy motor and brings the whole vehicle down.
Exactly.
The sources detail this cascading series of root causes, and it starts at the fundamental electrical architecture.
Right, at the board level.
Yeah. So in a dual motor setup, you have two main control modules. You've got the traction motor controller and the generator motor controller.
Right.
But to save on weight and cost and just physical space in the car, manufacturers highly integrate these systems.
They cram them together.
They do. They physically share the exact same low-voltage power rail on the circuit board. So the positive 5-volt and the 3.3-volt power supplies and their analog ground planes are identical.
Which, is standard practice for efficiency, but it creates a massive vulnerability when things go wrong.
Because they're tied together.
Exactly. Because when a motor fails in this context, we aren't usually talking about a loose wire or a bad ground. We are often looking at a catastrophic metallic short circuit inside the inverter.
A metallic short circuit.
Yeah, what the industry calls a desaturation overcurrent event.
Yeah.
The power semiconductors, whether they are IGBTs or silicon carbide MOSFETs, they are handling hundreds of volts and massive amounts of energy from the battery.
Right.
If they short out and just slam shut, the electrical current spikes violently.
And our sources specify exactly how violent. They measure this transient at up to 5 kiloamps per microsecond.
Yeah, let that sink in for a second.
That is 5,000 amps of high voltage energy shifting in 1/millionth of a second.
It's hard to even picture.
To put that in perspective, a standard house circuit breaker trips at, what, 15 or 20 amps?
Right, 20 amps and your lights go out.
And we are talking about 5,000 in a microsecond.
It is an incomprehensible amount of instantaneous energy. And when that 5,000 amp spike hits the high voltage side, it induces a severe reaction on the low voltage side, even with heavy filtering in place.
It bleeds over.
It does. It triggers a phenomenon known as ground bounce.
Okay, so this is where the shared architecture becomes a huge liability. Ground bounce essentially means the intense electromagnetic interference from that massive current spike injects common mode noise directly into the shared ground plane.
Right.
And we all assume that ground on a circuit board represents 0 volts, right? Like it's the baseline reference for every calculation the computer makes.
Yeah, it's the floor.
But during a 5 kiloamp per microsecond transient, the ground literally bounces.
The floor moves.
The 0 reference is physically elevated.
Exactly. And because the Healthy Motors controller is attached to that exact same bouncing ground plane, it's highly sensitive analog to digital converters, the channels reading the Healthy Motors speed and phase voltage and current, they suddenly see wild, impossible spikes in their data.
Even though the motor is fine.
Even though it's totally fine, the ground shifted, so the data shifts.
I guess it's like turning on a massive industrial vacuum cleaner in an old house,
Yeah.
causing all the lights to dim.
Yeah.
But wait, if the car is so advanced, why would they put both brains on the same circuit breaker, essentially?
Yeah. Well, again, it comes down to cost and packaging. You don't want 2 of everything if you can avoid it. But the trade-off is this ground bounce.
So the Healthy Motors brain just panics.
It absolutely panics.
It looks at the corrupted data and assumes, oh man, I must be experiencing a massive overcurrent or I've lost phase voltage.
Right. It thinks it's dying, too.
So it defensively shuts itself down to prevent what it thinks is its own destruction.
Yep.
And boom, the E04 failure mode triggers.
And the limp-home mode never even gets a chance to start.
Wow.
Because the healthy motor was essentially tricked into committing digital suicide by the electrical noise of the dying motor.
Tricked into digital suicide, that is intense.
It's an incredibly frustrating failure from an engineering perspective because the healthy motor was perfectly fine.
Yeah.
It was just blinded by the noise. But, and here's where it gets worse, that electrical shockwave is really only half the battle.
Oh, there's more.
Oh, yeah. Let's assume the engineers perfectly isolate the low voltage circuits. Let's say the healthy motor's brain somehow survives the initial electrical transient and tries to take over propulsion.
Okay, so it steps up to do its job.
Right. We immediately run into a severe mechanical reality.
Right, because these aren't just independent computers floating in a void somewhere.
No, they are very heavy physical things.
They are 2 massive physical motors bolted to the exact same drivetrain, usually linked through a planetary gear set and connected to the same axles.
Exactly. They are mechanically married.
So if the healthy motor takes over, it is physically forced to drag the rotor of the dead short-circuited motor at high speeds.
And this creates a catastrophic condition called uncontrolled generation, or UCG.
Uncontrolled generation.
Yeah, as the healthy motor drags the dead motor's rotor, the permanent magnets inside that dead motor are spinning rapidly past its short-circuited stator windings.
Which acts like a generator.
Right. According to Faraday's law of induction, this generates massive back electromotive force, or back EMF. But because the windings are shorted together, that electrical potential has nowhere to go.
It's just trapped.
It loops back on itself, generating a massive, steady-state short-circuit current inside the dead motor.
Which introduces 2 massive physical problems, according to the sources.
Yeah.
The first is a parasitic electromagnetic drag torque.
Right.
The magnetic force is pushing back against the rotation, become incredibly strong. The dead motor essentially turns into a massive electromagnetic anchor.
A literal anchor, yes.
And the drag torque can actually become so severe that it exceeds the healthy motor's maximum pushing power.
Wow.
So the healthy motor tries to push, the dead motor pulls back harder, and the vehicle physically stalls out on the highway.
While you're trying to go 70.
Right.
The physical forces are just immense. But the second problem that uncontrolled generation causes is thermal.
Heat.
Massive heat. All that looping short-circuit current generates severe joule heating. The math behind it, it's I squared R, means the heat goes up exponentially with the current.
So it gets hot fast.
Very fast. The source document notes that within mere seconds of this drag state, the internal temperatures skyrocket. Seconds. It gets so hot that the enamel insulation coating the copper wires inside the stator simply melts away.
Oh, man. And once that enamel melts, the high-voltage energy inside the dead motor can just arc across parasitic capacitance.
Yeah, it finds a path, yeah.
It shoots high-voltage spikes back up the line, bypassing all those initial protections we talked about, and literally burns out the low-voltage control board anyway.
Okay, it gets it in the end.
So the mechanical drag creates a thermal runaway that loops back and destroys the electronic brain.
The physical failure infects the software.
It's like a horror movie for engineers.
It really is. Which brings us to the software itself.
Oh, right, the brains.
Yeah, even if the hardware doesn't literally melt, the code running the car can suffer a complete architectural breakdown.
How did that happen?
Well, modern EVs don't use simple processors. They use highly advanced multi-core microcontrollers. The document explicitly references architectures like the AURIX TC397. Okay.
To handle the incredible processing speed required for vector motor control, the tasks are strictly divided. Core 0 might run the traction motor. Core 1 runs the generator motor. Core 2 acts as the supervisor, managing the state machine, the safety diagnostics, and just the overall vehicle logic.
It's a system built on extreme delegation.
Highly segmented.
Yeah. But when a massive failure happens, that delegation becomes a huge bottleneck.
Exactly.
The supervisor, Core 2, detects the dead motor. It has to instantly coordinate a totally new reality across the other cores.
Right, it's the boss shouting orders.
It has to command Core 1 to shut down and enter an active short-circuit state. And it has to command Core 0, hey, you are now carrying the entire weight of the vehicle. You are cleared to output double your normal peak current.
And it has to do this perfectly.
Right. It sends these critical instructions via interprocessor communication, or IPC.
Then IPC is heavily reliant on timing.
When you have multiple processor cores accessing the exact same shared memory registers to read and write instructions, you have to use strict, thread-safe software protocols.
Otherwise, they trip over each other.
Exactly. Engineers use what are called atomic operations, or hardware locks, known as mutexes. If these aren't perfectly implemented, you get a race condition.
A race condition. I think the best way to visualize a race condition in this context is to think about writing a word on a whiteboard while someone else is trying to read it at the exact same time.
That's a good analogy.
Let's say Core 2 needs to write a complex 32-bit instruction into memory for Core 0 to read.
Okay.
But Core 2 can only write 16 bits at a time, so it writes the first half. But before it can write the second half, Core 0 swoops in and reads that memory block.
Oh, so it gets garbage.
Right, Core 0 just read half of a new instruction and half of an old instruction. In computer science, they call this data tearing.
Data tearing. And it is a fatal error in vector control. Core 0 reads that torn, garbled piece of code and essentially throws its hands up.
It doesn't know what to do.
It has no idea. So it hangs in a pending state. Or worse, the cores get deadlocked, infinitely waiting on each other for permission to proceed that will literally never come.
Like two people trying to grab the steering wheel at the exact same time without communicating?
Exactly.
Are you telling me that without a strict, talking stick protocol, the cores just freeze up and wait while the car is driving?
Yes. And while the cores are deadlocked, remember, the car is still moving at 70 miles an hour.
Oh, my God. But the system has a built-in referee for this, right? The watchdog timer.
Right, the watchdog.
If the watchdog timer sees that the cores haven't executed a valid instruction in a few milliseconds, it assumes the software has totally crashed.
Yep.
So its hard-coded response is to trigger a total system reset.
It pulls the plug.
It reboots the brain. So a race condition in the IPC causes a total brain reboot while the car is in motion.
Yeah.
Limp-home mode fails to activate, and E04 triggers again.
It is a domino effect of logic failures. Just one thing knocking over the next. And there is one final domino that can fall, which involves how the car tracks the physical position of the motors.
Okay, position tracking.
Precise vector control requires knowing the exact electrical angle of the motor's rotor at all times.
Down to the fraction of a degree.
Exactly. Normally, physical sensors, they're called resolvers, they do this job. But if the physical sensors fail or the data is corrupted by that ground bounce we discussed earlier, the system falls back to sensorless mode.
Right. Sensorless mode uses sliding mode observers. Essentially, the computer uses complex math monitoring the voltage and current to estimate exactly where the motor is, even without a physical eye on it.
It is a brilliant backup plan.
It really is.
But it relies heavily on thermodynamics remaining constant.
Physics gets in the way.
Always. Let's say this motor failure happens while you are pushing the car to its absolute limits, like a full throttle acceleration up a steep grade, pulling a heavy load.
Towing a boat up a mountain.
Exactly. Under those extreme demands, the internal temperature of the motor can easily exceed 130 degrees Celsius.
That is cooking.
It is. And at 130 degrees Celsius, the laws of physics start altering the fundamental properties of the motor itself.
How so?
As the copper stator windings heat up, the increased thermal energy causes greater electron scattering.
And the source data is very specific about the severity of this divergence. Because of that thermal drift, the computer's estimated electrical angle can diverge by more than 45 degrees from the true physical angle of the rotor.
45 degrees is a massive miss in vector control.
It is. If the computer is off by 45 degrees, it is firing high voltage energy at completely the wrong time.
Right.
The control vectors are perfectly misaligned. Instead of pushing the rotor forward smoothly, the magnetic fields clash violently.
Oh yeah, they fight each other.
It causes massive shuddering vibrations throughout the drivetrain. Those vibrations trigger immediate overcurrent protection circuits in the inverter, and the system shuts down.
Again.
The backup sensorless math literally hallucinates itself into a catastrophic failure simply because it couldn't adapt to the heat.
It's a perfect storm. I mean, think about it. You have bouncing ground planes corrupting data.
Right.
You have mechanical drag melting the wiring.
Yeah.
You have multi-core software deadlocking itself into a reboot. And then backup math hallucinating due to extreme heat.
It's a miracle these things drive down the street.
It really is. To stop this cascading E04 failure, automotive engineers are bound by the rigid mathematics of the ASIL D standard.
Okay, so how do they fight back?
They operate under a strict metric called the fault-tolerant time interval, or FTTI.
The FTTI, okay, so I read about this. The FTTI is basically the absolute maximum time the system is allowed to take to mitigate a hazard before it becomes critical.
Right, before the driver notices or crashes.
And our sources state that for this dual motor system, the FTTI is astonishingly small.
Tiny.
The vehicle has a maximum of 60 milliseconds to completely identify and physically cut off the failing motor.
60 milliseconds.
And within that window, it has exactly 5 milliseconds to successfully reconstruct the software for the healthy side and take over propulsion.
5 milliseconds to rewrite reality.
We're talking about orchestrating a massive mechanical and digital shift in a fraction of a blink of an eye.
To achieve that speed, they can't rely on just like a single layer of protection. They layer multiple parallel defense mechanisms.
It's like a defense in depth.
Exactly. The first defense targets that initial electrical chaos, the ground bounce.
Bouncing floor.
Right. They use microsecond voltage gating.
Okay.
The system doesn't wait for a data channel to report an error. That takes too long. It constantly monitors the raw analog reference voltage windows, the VREF, at the absolute hardware level.
So it's looking for absolute stability on the power line itself.
Yes.
If that reference voltage deviates by even 1.5%, the system immediately knows the ground plane is compromised.
It doesn't even ask questions.
It doesn't query the software at all. A dedicated hardware safety management unit, the SMU, steps in automatically.
And it reacts in just 10 microseconds?
10 microseconds.
10 microseconds is effectively instantaneous in mechanical terms. When the SMU detects that tiny voltage ripple, it immediately isolates the healthy motor's critical data channels.
It cuts them off from the bad ground.
Right. It switches their power supply over to a backup, heavily shielded source called a band gap reference.
A band gap reference.
Yeah, this is a highly stable voltage reference that is largely immune to temperature and common mode interference. By switching to the band gap reference in 10 microseconds, the healthy motor's data stays pure.
Oh, wow.
It completely ignores the 5,000 amp electrical chaos happening just millimeters away on the same board.
So it basically puts impenetrable noise-canceling headphones on the healthy motor before the electrical explosion even fully registers.
That is exactly what it does.
That solves the false panic shutdown. But what about the mechanical drag? How does the healthy motor know if it's safe to push without stalling out from that parasitic magnetic anchor?
Right, because if it pushes too hard against the dead motor, you still stall.
Right.
This is where the engineers utilize incredibly fast drag-torque math.
Drag torque math.
While the hardware is gating voltages on one side, The software is running a dedicated hyper-fast calculation cycle every 100 microseconds. Without relying on physical torque sensors, because those can break, it uses the voltage and current data to constantly estimate the exact mechanical drag torque being produced by the dead motor.
It's mathematically weighing the parachute while running.
That's a great visual.
Yeah. And the engineers established a hard physical limit. If that estimated drag torque hits or exceeds 70 newton meters, the system mathematically proves that a safe physical isolation is impossible.
The anchor is just too heavy.
The dead motor will overpower the healthy one. So when it hits 70 newton meters, it stops trying to limp home.
It gives up on limping.
It instantly triggers a specific diagnostic trouble code,
Yeah.
DTC P0A7F,
P0A7, right.
which officially declares the degradation mode invalid. It then shifts to a completely different fail-safe protocol, intentionally cutting propulsion to all wheels evenly to prevent that asymmetrical, unexpected brake lockup we talked about.
Right. It sacrifices the drive to save the stability of the vehicle. You coast instead of spin out.
Exactly.
But, what if the issue is inside the software itself? We discussed the IPC race conditions and the data tearing. If the main cores are deadlocked, how does the system execute any of these safety protocols?
Here's where it gets really interesting. The functional safety engineers essentially accept that during a catastrophic failure, software is inherently fragile.
You can't trust the code when the processor's melting.
Right. They build a defense mechanism that fundamentally does not trust the multi-core software to do the most important job.
I love this part.
They utilize a doer-checker lockstep architecture, backed up by a completely external, independent piece of hardware called a system basis chip, or SBC.
The doer checker setup is just brilliant.
Tell me about it.
So Core 0 and Core 1 are the doers. They are out there executing the complex motor control.
Driving the car.
Right. A separate core, or a totally separate checker module, constantly verifies the math and the memory registers of the doers.
Like a hall monitor.
Exactly. If the checker detects any discrepancy, like a memory parity error, data tearing, or that race condition we talked about, it knows the main microcontroller is compromised.
And crucially, the checker doesn't try to send a software command through that corrupted microcontroller to shut down the inverter.
Because it knows the software pathways are dead.
Right. Instead, the checker communicates directly with the external SBC, and the SBC has a physical hardware pin, like an actual direct copper trace, wired straight to the gate drive power supply of the failing motor.
A hard line.
When the SBC gets the kill signal, it bypasses the entire software stack and physically cuts the power to the gate drive within 1 millisecond.
1 millisecond. It is the ultimate failsafe. You don't ask a crashing computer to run a shutdown script.
Right. You don't say, please turn off.
Exactly. You build a separate, tiny, hyper-reliable chip whose only job is to physically pull the plug on the high voltage flow the moment the main brain stutters.
It forces the broken motor into a safe, unpowered state entirely via hardware. It's like, instead of asking a malfunctioning robot to turn itself off via a command line, you just pull the physical plug out of the wall.
Beautifully simple, yet incredibly complex to engineer.
Which isolates the danger perfectly. But now the healthy motor is alone, and it has just a few milliseconds to take over all the propulsion without causing a massive, violent jerk that could cause the driver to lose control.
Right, because if you suddenly shift all torque to one axle, the car is going to swerve.
How do they smoothly transition from two motors driving to one motor driving in under 5 milliseconds?
They do it through an S-curve transition algorithm, which relies on something called shadow mode.
Shadow mode.
Yeah. The healthy motor's controller isn't just sitting there waiting for an emergency. Even during normal, perfect driving, it runs a parallel calculation in the background.
Oh, wow.
It is constantly calculating the exact vector control parameters it would need to keep the car moving at the current speed and trajectory if it were operating completely alone.
So it's constantly syncing a parallel reality.
That's shadow reality, yeah.
When the SBC pulls the plug on the dead motor, the healthy motor doesn't have to waste precious milliseconds calculating a new torque demand from scratch.
It already knows what to do.
He just seamlessly adopts the shadow mode data it was already calculating, but jumping instantly to that higher torque demand would still snap your neck, wouldn't it?
Exactly. A step change in torque is mechanically violent. So the software applies an S-curve mathematical blending filter over a tiny window of 3 to 5 milliseconds.
Okay, an S-curve.
Instead of a sharp vertical cliff of power delivery, the torque ramps up along a smooth parabolic curve.
The sources are very specific about the result of this S-curve math. By blending the torque over those 5 milliseconds, they limit the actual mechanical torque vibration felt at the wheels to less than or equal to 5 Newton meters.
5 Newton meters is barely perceptible.
Right. You could have a full cup of coffee on the dashboard, lose half your powertrain to a catastrophic short circuit, and you wouldn't even spill a drop.
It's amazing.
You would just feel a seamless, smooth reduction in overall acceleration as the vehicle safely enters limp-home mode.
And just to be safe, limp-home mode electronically caps the vehicle's speed at 40 kilometers per hour and limits torque to 30% of its maximum.
Just to guarantee you can safely maneuver off the highway without overloading the surviving hardware.
The choreography is astounding. It's a ballet of electrons.
It really is. But functional safety, achieving that ASIL D rating, it isn't just about reacting perfectly when things explode.
No, it's about making sure they don't explode in the first place.
Exactly. It is equally about obsessively designing the hardware and the manufacturing process so that these specific failures are mathematically improbable from the start.
Right.
Our sources outline this through rigorous DFMEA, PFMEA, and DVP&R protocols.
Alphabet soup, but incredibly important.
Let's start with the design phase. The Design Failure Mode and Effects Analysis, or DFMEA. This is where engineers stare at blueprints and literally try to break them.
They look for every possible weakness.
We talked earlier about ground bounce, right? The danger of sharing a power supply.
Right, the bouncing floor.
To mitigate that at the design level, engineers utilize a technique called mote isolation.
Mote isolation. It is exactly what it sounds like.
Yeah.
On the physical multi-layer PCB, the printed circuit board, they actually carve a physical gap, like a moat of empty fiberglass, between the power domains of the two motor controllers.
They physically separate the grounds.
They draw a line in the sand.
But they still need to communicate, right?
Yeah.
So they bridge that physical moat using highly specialized high-frequency magnetic beads and optoisolators.
Right.
This means data can cross the moat, but massive electrical transients cannot.
The noise gets stopped at the wall.
This physical isolation architecture guarantees that even during a 5,000 amp short circuit on one side, the voltage fluctuation on the healthy side's VREF stays under 0.2%.
Which is basically nothing.
Total physical isolation.
It is highly effective. But, the most impressive DFMEA innovation in the document, in my opinion, addresses the thermal drift problem we discussed.
Oh, where the backup math hallucinates because the motor hits 130 degrees Celsius.
Yes. Instead of trying to write infinitely complex math to predict thermal dynamics in real time, the engineers sidestep the problem entirely using an active search coil technique.
Okay, this is genuinely one of the most brilliant engineering pivots I've ever read about.
It's so smart.
When a motor fails and the SBC physically cuts its power, its copper stator windings are just sitting there, dead and unpowered, wrapped around the rotor.
Right, they're just dead weight.
The healthy motor is now spinning the vehicle, which means it is also spinning the permanent magnets inside that dead motor.
Because they're physically connected through the wheels.
Exactly. And spinning magnets induce a magnetic field.
Always.
So the system uses high-voltage contactors to fully isolate those dead windings from the main bus. Then it repurposes those dead windings. It uses them as a massive physical antenna to read the pure back EMF generated by the spinning magnets.
They literally turned the dead motor's leftovers into a makeshift, hyper-accurate physical sensor for the healthy motor.
That is engineering wizardry.
It really is. Because there is no high-voltage current flowing through the dead windings, there is no electrical noise.
Wow.
And because they are just measuring raw magnetic induction, the extreme 130-degree heat doesn't skew the data.
They completely bypass the mathematical thermal drift by turning a liability into a perfectly clean sensor mid-crisis.
That is the absolute essence of resilient design. You use what you have.
Incredible. But an elegant design on paper means nothing if it is assembled poorly in the factory.
Very true.
That is where PFMEA comes in. Process failure mode and effects analysis.
The manufacturing side.
The factory floor has zero tolerance for microscopic errors, particularly when soldering the high-power chips to the board.
Because a bad solder joint on a 5,000 amp circuit is a bomb.
Exactly. Our sources specify the use of 100% automated X-ray inspection, or AXI.
X-rays.
Every single critical solder joint on every single board is hit with a 3D X-ray before it leaves the line.
Wow.
They are looking for voiding, microscopic air bubbles trapped inside the metal solder during the reflow process.
And they care about bubbles that small.
The tolerance is incredibly strict. If the total void area across a chip exceeds 5%, Or if a single pin has a void larger than 1%, the entire board is rejected.
Because a 5% air bubble might conduct electricity fine at room temperature.
Right.
But when that board experiences the extreme thermal cycling of an EV, like heating up to 125 degrees and cooling down to sub-zero, that tiny air pocket expands and contracts differently than the metal around it.
It stresses the joint.
Exactly. Over thousands of miles, that 5% void propagates into a microscopic fatigue crack.
And then what?
That crack increases resistance, disrupts the signal, and eventually triggers the exact E04 failure we've been discussing.
So they are hunting for microscopic futures of failure.
They have to.
They apply the same extreme paranoia to the physical connectors using vibration armor.
Vibration over, yeah.
An EV drivetrain vibrates intensely. To combat this, they mandate the use of heavy-duty mechanical strain relief brackets and mandate gold-plated pins on the critical logic connectors.
Gold.
Gold is highly conductive and doesn't oxidize.
Ah.
Furthermore, they clamp these connections so aggressively that the relative movement between the pins under maximum vibration is limited to less than or equal to 1 micrometer.
1 micrometer of movement. That's 1,000th of a millimeter.
It's nothing.
They enforce that to eliminate a phenomenon called fretting oxidation.
What's that?
When non-precious metals vibrate against each other, even microscopically, they scrape off their protective oxide layers.
Oh, I see.
The raw metal oxidizes again, gets scraped again, and eventually builds up a microscopic layer of rust that acts as an insulator.
A layer of rust acting as an insulator on a logic pin.
Right. That rust can momentarily block a critical 5-volt signal during a highway maneuver. By restricting movement to a single micrometer and using gold, they engineer fretting oxidation out of existence.
And after they design it perfectly and build it perfectly with X-rays and gold, they still don't trust it until they try to destroy it.
The final step.
The final validation phase is the DVP&R, Design Verification Plan and Report.
The torture test.
Every single dual-motor powertrain undergoes a brutal end-of-line test before being cleared for a vehicle. They mount the system on a dynamometer, spin it up to maximum operational speed, and the computer intentionally injects a violent short-circuit fault directly into the traction motor.
They force the system to experience the exact catastrophic failure it was designed to prevent.
On purpose.
Yes. And automated sensors track the response. They verify that the SBC pulls the pin, the voltage gate shut, the shadow mode imports the data, and the S-curve algorithm takes over, all strictly within that 5-millisecond window.
They test it on every single one.
Every single one. They also verify that the physical torque ripple at the output shaft stays below that 5 Newton-meter limit. If any parameter fails by a fraction of a millisecond, the production line halts.
But the validation during the design phase goes even further, right?
What's further?
They subject the running controllers to an electromagnetic torture chamber. They blast the active logic boards with 200 milliamps of raw radio frequency noise to simulate extreme EMI environments.
Just blasting it with noise.
They bake the controllers in rapid thermal shock chambers, cycling them from negative 40 degrees Celsius up to a blistering positive 125 degrees Celsius, while simultaneously violently shaking them on a 3-axis vibration table for over 1,000 uninterrupted hours.
If the hardware and software can maintain that 5-millisecond fail operational window while being baked, frozen, irradiated, and violently shaken for 1,000 hours, it earns the ASIL D rating.
It survives the gauntlet.
It does.
So what does this all mean? We started this deep dive looking at a deeply concerning concept, E04, Single Motor Degradation Mode invalid.
Right.
The idea that a single hardware short could deadlock the software, trick the backup sensors, and lock up your wheels at highway speeds is terrifying.
Very.
But pulling back the curtain on this source document changes the perspective entirely. This proves that true automotive engineering isn't just about making electric cars accelerate fast or, maximizing battery range.
No, it's about the safety nets.
Real engineering is the obsessive, microscopic orchestration of how things fail.
Exactly.
It's carving digital motes in fiberglass, pulling physical pins in less than a millisecond, and seamlessly blending mathematical parabolas so that when the system suffers a catastrophic heart attack, the driver simply thinks, the car feels a little sluggish, I should probably pull over.
It is a profound level of invisible protection. However, there is one final detail buried at the very end of our source document that caught my attention. This raises an important question.
Oh, what was tucked away at the end?
The author concludes by noting that they are providing the engineering teams with a highly complex software tool to design these systems. They describe it as a Python transient electrothermal mechanical dynamic coupled simulation model.
A coupled simulation model.
Yes.
So they have a Python program powerful enough to simulate the electrical spikes, the thermal melting, the mechanical drag, and the multi-core software logic, all interacting with each other simultaneously in a virtual environment.
All at once.
They simulate the exact microsecond dual-core system deadlocks or the exact degree of thermal drift, purely in code before a physical prototype is ever built.
Exactly. It allows them to iterate fail-safes virtually. But here's the thought I want to leave you with.
Okay.
Currently, these massive coupled multi-physics simulations are run on powerful engineering workstations during the design phase. But processing power inside the vehicles themselves is growing exponentially.
That's true.
How far away are we from a reality where the EV's onboard computer is running these exact predictive Python simulations live in the background while you are driving?
Wait. You're suggesting the car could run a continuous digital twin simulation of its own powertrain in real time?
Think about it. The car knows its own temperatures, its own voltage fluctuations, the exact microscopic wear and tear on its components.
Yeah.
What if it feeds that real-time data into a live simulation model? It wouldn't just be reacting to a 60-millisecond FTTI after a wire snaps.
Oh.
It could simulate its own degradation and predict the exact moment an E04 limp-home failure is mathematically guaranteed to happen hours, days, or even weeks before the physical wire actually breaks.
It would predict the failure before it ever physically manifests.
Yes.
It would just calmly display a message on your dashboard on a Tuesday morning saying, based on current thermal and electrical degradation models, traction motor A will experience a desaturation overcurrent event in approximately 400 miles. Please route to a service center.
It shifts the entire paradigm from reacting in microseconds to predicting in months.
That is where this technology is heading. It is an incredible, invisible war fought with math, physics, and extreme paranoia, and it's happening every single time we press the accelerator.
It really makes you appreciate the engineering.
Thank you for taking this deep dive with us. Keep your eyes on the road, and remember to appreciate the millions of micro decisions keeping you safe along the way.